Hello everyone, I'll be presenting our SoK on vulnerabilities in TrustZone TEs. This is joint work between me, David Cerdeira, Nuno Santos, Pedro Fonseca and Sandro Pinto. TrustZone is a hardware-based technology built into ARM processors. It enables the deployment of security mechanisms present in most mobile devices out there. These mechanisms are assumed to be highly secure, often being trusted with cryptographic key storage and operation. Furthermore, they play a major role in providing a secure data path. However, the sad reality is that these systems have been successfully attacked multiple times, which has enabled attackers to retrieve the device's disk encryption keys, for example. Attacks like this reveal that millions of devices were, and likely still are, at risk. It's necessary to have an in-depth look at what makes these systems vulnerable, to pave the path for more secure TEs. When we set out to study TrustZone TE vulnerabilities, we obtained information from multiple sources, and it was challenging to have a broad enough picture of the state of affairs on the security of these systems. So, we gathered reported vulnerabilities from various sources, totaling over 200 vulnerabilities to analyze. We created a classification scheme with three main categories, and classified the vulnerabilities to better understand them. We then identified the main issues and looked at how the research community is addressing them. In this presentation, I'll talk about each of these points. Let's talk about gathered vulnerabilities first. Because reported TE vulnerability information is widespread, we got our data from many different sources: CVE databases, proprietary databases, scientific papers, internet posts, and source code and repository history. And this led us to identify over 200 vulnerabilities. From these vulnerabilities, we learned that all major TEs have been compromised at some point. We also learned that most of the reported vulnerabilities severely affect system security, with most vulnerabilities scoring severe or critical classifications. Furthermore, all secure software layers have shown themselves vulnerable. These facts raise questions on the security guarantees that these systems actually provide. In the process of analyzing security vulnerabilities, we classified issues into three large categories: TE architecture, implementation, and hardware. Now, I'm going to talk about these issues starting by the architectural problems. What we consider to be architectural problems are problems that arise from the design decisions, including interaction between components. If we take a look at the picture on the right, we see the overall TE software architecture. The normal world components, the user-facing applications and the operating system which supports them. And then we have the secure world components, the secure monitor, which is the highest privileged piece of software in the system and is mainly responsible for performing context switch between the worlds. The trusted OS, which runs in a similar level of privilege as the normal world OS, but in a secure world. And there's the trusted applications. The trusted applications provide most of the security functionality expected from the secure world, implementing features such as the user authentication or cryptographic key management. These are some of the issues identified in regard to TE system architecture: widespread interfaces in the TE system components, which we'll talk about in a second, excessively large TCBs in the TE, trusted applications having access to high privilege functionality such as being able to map the normal world, lackluster implementation of memory protection mechanisms such as tag cookies, poor implementation of trusted applications, among others. Now, let's see some examples of these issues. We'll start by seeing how wide interfaces in the TE systems promote designs more prone to security vulnerabilities. These wide interfaces are an issue in both the trusted OS and trusted applications and presents itself in three main ways. The first is in the number of trusted applications and in the number of commands that trusted applications expose to the normal world. For example, in a particular release of the Qualcomm TE, the YVTA, which is part of a DRM implementation, exposes 70 different commands, and most of them manage complex data structures. With this being said, it's not surprising that vulnerabilities have been found in them. The second way TE interfaces might lower the TE security is by having the trusted OS providing trusted applications with access to too many system calls. For example, the Qualcomm TE provides 69 different system calls to its trusted applications. Some of these system calls effectively give high privileges to the trusted applications. For example, by giving them access to map normal world memory, trusted applications can compromise the normal world OS. Third, secure device drivers may be accessible to more trusted applications than required for the system to perform its functions, which can prove instrumental to building powerful attacks. For example, in the Trustonic TEs, virtually every trusted application has access to the fingerprint device driver, which might compromise user authentication. Now, let's look at the problem of excessively large TE DCBs. The way we approached this issue was by counting the lines of code of the trusted OSs when available, and to measure binary sizes of both the trusted OSs and the trusted applications. We compared the TCB of the trusted OSs to SEL4, as SEL4 is a security-driven microkernel. We can see that the overall trusted kernels are fairly larger than SEL4. Looking at the TCP for trusted applications, we can see that they present megabytes of code that needs to be trusted alongside the trusted OSs. Both these facts led us to conclude that TEs are big and complex. Now I'll talk about why trusted applications being able to map normal world physical memory helps compromise TEs or the system. Certain applications require an efficient shared memory mechanism that allows for exchanging high volumes of data across worlds with low latency. To this end, TEs implement functionality that allows them to map normal world. For example, Qualcomm TE provides a system call that allows any trusted application to map any physical memory belonging to the normal world, including the normal world kernel. The TrustZone TE does not allow trusted applications to map physical memory. Trusted applications must issue a request to a dedicated driver. A whitelist is used to prevent access to this feature. However, the whitelist is hard-coded in the driver, and the number of allowed trusted applications reaches 34. Mapping the normal world is a mechanism that can easily be abused for privilege escalation. By compromising a trusted application that can map the normal world, an attacker may also completely compromise it. The next architectural issue is a lackluster implementation of memory protection mechanisms. This is a problem that's mainly present in trusted OSs and trusted applications, and which facilitates the exploitation of other vulnerabilities. Modern OSs employ various memory protection mechanisms to protect themselves against possible vulnerabilities in their code. These mechanisms include address space layout randomization, stack canaries, page guards, and execution protection. We found that TE systems only partially implement these measures, as you can see on this table, mostly filled by empty circles. Address-based layout randomization makes attacking loadable code harder by requiring the attacker to guess the position of vulnerable code. Stack cookies and page guards protect against buffer overflows, and execution protection prevents memory pages mapped as writable from being executable. The last architectural issue I'll be talking about is trusted application revocation, which is an issue within the trusted OS. It is common for TEs to load trusted applications from the normal world file system. This makes them easier to install dynamically and to update them, for example, to fix security vulnerabilities. One of the measures TEs take to prevent any application from running in the secure world is digitally signing approved trusted applications. After trusted applications have been patched, it means that all known vulnerable versions of these applications cannot be allowed to run on a TE, which would risk compromising the security of the trusted service or even the security of the system. To prevent this, TEs must revoke trusted applications from running. However, researchers have found it possible to load vulnerable versions of trusted applications within the Qualcomm and TrustZone TEs, and this has allowed researchers to compromise supposedly patched versions of TE systems. Our next topic is implementation issues. These are issues not in the way TEs are designed, but in their actual implementation. These are the types of implementation issues we found in our analysis. Validation bugs all over the TE, from bootloaders to secure monitor, trusted OS, and of course trusted applications. Bugs configuring memory protection and peripherals, bugs implementing security mechanisms, and bugs more related to external factors such as concurrency and software side channels. Let's talk about the validation bugs first. Validation bugs involve improper handling of input and output values. Improper validation of these values leads to buffer overflows, use of unexpected parameter values, and mishandled integer overflows, for example. Validation bugs occur in all secure software components. Trusted applications, which comprise most of the code in the TE and implement complex features, so this is not too surprising. Trusted OS, which has access to all system resources and whose compromise severely affects the system platform, and even in the highest privileged software, the secure monitor. What's more surprising is that even error-checking code might be buggy. The example I'll show you shows a validation bug within the secure monitor. The secure monitor is the highest privileged piece of code in the system, and by exploiting a bug in the secure monitor, an attacker can automatically gain full control of the device. This bug was present in the ARM trusted firmware, which is ARM's reference implementation for secure monitor software. This implementation is often configured by vendors to meet their particular needs and is incorporated as part of their TE solution. Let's take a look at the bug. Ironically, this bug was present in a macro whose purpose is detecting overflows when doing pointer arithmetic. This macro failed to detect overflows of 32-bit pointers when the software was built for 32-bit platforms. This is because the unsigned int pointer max define was set for the maximum 64-bit pointer value and not for the maximum 32-bit pointer value as it was supposed to. Next, we look at what we call functional bugs. Functional bugs are errors caused by inconsistencies between the implementation and the program specification intended by the programmer. An instance of these types of problems was found in the ARM Trusted Firmware Secure Monitor implementation. It was caused by misconfiguring the memory page table attributes when setting up the page tables for the Trusted OS. The property set disabled the execute never feature of the memory management unit and allowed read-only memory pages in the Trusted OS to always be executable. In the right circumstances, it could have led to attackers gaining unexpected code execution. Now, let's take a look at an example of extrinsic bugs. Extrinsic bugs are bugs that are caused by the improper handling of external factors. We have as an example a concurrency issue which appeared in the opt-in trusted OS, which failed to correctly handle the simultaneous execution of two trusted applications accessing the file system. opt-in allows simultaneous execution of applications by leveraging the multiple cores on the platform. And by allowing two applications to simultaneously access the file system, it was subject to a race condition in which a running trusted application could delete a file system directory which another was accessing. This led to unexpected behavior and could cause loss of security-sensitive data. Now, let's talk about the hardware, the last main source of errors in TEs. TE programmers must be aware of the effects of interfacing the hardware components and must also consider the microarchitectural behavior of the platform in which they execute. These are the hardware issues we identified in TEs. It's possible to attack TEs by leveraging reconfigurable hardware components and by maliciously manipulating energy management mechanisms. Also, it's possible to obtain secrets from the TE by exploiting cache side channels, hardware buffers, and performing cross-world rowhammer attacks. Let's look at a couple of these problems. Energy management mechanisms can be used as a means to break the normal world, secure world TrustZone isolation. Here, we reference the corkscrew paper, but there's also a more recent work which came out after our paper was accepted, Volchocky. In corkscrew, the authors leverage the fact that normal world software is the one responsible for energy management. The normal world has access to the energy management hardware and can set voltage and frequency values. However, as you can see on the figure on the right, it's possible to go way above the recommended values. And these enable attackers to make the CPU operate in a high probability state of performing faulty operations. And what this means is that the normal world can inject faults in the secure world, and this can be leveraged to extract secrets, such as cryptographic keys. The other hardware problem I'm going to talk about is the leakage of information through caches. TrustZone creates two environments which share the same hardware, and as we know by now, sharing hardware resources is a surefire way to leak information. In TrustZone, even though the secure data in the caches is not accessible to the normal world, the cache lines within the cache are contended by both worlds, meaning that both worlds compete for their utilization. This enables attackers to mount prime and probe attacks, where they first put the cache in known state, trigger the secure world to execute, and then assess the cache state. This technique can allow attackers to retrieve secrets such as cryptographic keys. We've looked at how TAs are vulnerable. Now let's see how attackers might exploit these vulnerabilities. An attack typically starts from the normal world. To communicate with the secure world, the normal world often implements a device driver. This device driver may be exposed to all applications or implement a whitelist to only allow a select few to access it. When you're an attacker, you want to be able to access this driver. And although you may be able to do so from any application, it's more likely that you'll need to compromise the privilege process. It may be the case that the privilege process is fairly large, and so prone to vulnerabilities such as the media server in Android. Alternatively, you could try to gain kernel access in any way you see fit, but in the end, you want to have access to the communication driver. With access to this driver, you can now start probing the secure world for vulnerabilities. You'll select a trusted application as your target. The larger the trusted application, the more complex it probably is, and the more likely it is that you'll find a vulnerability in one of its multiple commands. One thing you might want to check is to see if you can make the trusted application arbitrarily access the normal world. And if you can, you may proceed to perform a boomerang attack on the normal world. This is useful if you launch your attack from outside the kernel itself. If you cannot perform a boomerang attack, or you already have kernel execution privilege, you can try to probe the TrustZone for vulnerabilities. To do this, you'll test the various system calls available to you, and you'll probe which drivers you can access from the TA which you've exploited. Luckily, you found a TrustZone vulnerability and were able to leverage it to gain execution privileges. You can now access any memory you'd like. You can use this privilege to read secrets from other TAs or access any device you want in the system. The platform is now fully compromised. So thankfully, the research community has been pretty vigilant and many solutions have been proposed to address many of the problems we talked about. Architecture-wise, we point out the support for multiple TEs by creating multiple environments. These environments allow OSs and their trusted apps to be isolated from other trusted OSs and their apps. The goal is preventing flaws in a certain app or OS from affecting another or from affecting the system. Researchers have also proposed encrypted memory to prevent against code boots or bus snooping. Implementation-wise, researchers have proposed the use of managed code runtimes in the secure world and the use of safe programming languages such as Rust to mitigate some of the implementation vulnerabilities in TE software, as well as the use of formally verified software within the secure world. Hardware-wise, to mitigate against energy attacks, safe operational values should be hardwired, for example. As for microarchitectural countermeasures, to prevent cache side channels, researchers propose the careful implementation of security-sensitive operations such as cryptographic algorithms and performing adequate cache maintenance. In conclusion, we've gathered vulnerabilities from multiple sources and have shown enough evidence to put the security TE systems provide into question. We've analyzed the vulnerabilities and learned that there's issues in architecture, implementation, and hardware of these TEs. Lastly, we've shown that there's an active research community which is addressing these problems. Thank you for listening. I'll now be answering some of your questions.